Hello, calculus class. I'm sorry I couldn't be with you. My kid is sick today, so I am home wishing I could teach you guys about our next technique, which is integration by parts. So that is technique number 2. Hopefully you guys still remember exactly what we did yesterday, which was the technique of substitution. Always look for that first, okay, before you go to any other techniques. No, look for substitution. And how do you look for substitution? Well, you look for the integral of perhaps a composition of functions, but also at times a derivative of the inside multiplied on the outside, because that is how you differentiate the composition of functions. So when we anti-differentiated that, we found that the result was the antiderivative of the outermost function, f, evaluated at g of x, plus some constant. So when we move into integration by parts, we'll be talking about how we undo really the product rule. But before we do that, let's take a look at a couple warm-ups in addition to the development of some new formulas for the integrals of some trig functions. Namely, the integral of secant of x, the integral of cosecant of x, and the integral of cotangent of x. So I will start you off, since these first two can be really rather tricky. You should probably consider writing the secant as secant of x times, now this is going to be really interesting and you might be able to see why I'm doing what I'm doing, but this little trick allows you to actually integrate the secant using the substitution technique that we talked about yesterday. So I'm going to say that secant of x times secant of x plus tangent of x over secant of x plus tangent of x. I'll let you look at that for a minute and decide why that might be helpful. And meanwhile, I'll say for the cosecant of x, we would like to do something very similar, which is multiply the cosecant by cosecant of x plus cotangent of x over cosecant of x plus cotangent of x. I'll put that in full parentheses, dx. And the cotangent of x, that one's pretty straightforward. You know how to rewrite cotangent of x, excuse me, as cosine of x over the sine of x dx. Now, all of these have very, very similar techniques here in the end. The cotangent of x is pretty self-evident. I mean, you can kind of see where this one's going. It's very similar to the integral of tangent, which we did yesterday. In that, now you can let w equal the sine of x, and dw then is equal to cosine x dx. So this integral becomes the integral of 1 over w dw. And that in turn is the natural log of the absolute value of w plus c. But w was simply sine of x. Okay? So that actually turns out to be the integral of cotangent of x. Now back up to these guys here. Did you guys discover or look at this more closely and say, why would we multiply by this disguised version of 1. It's really rather weird. Well, if you multiply this out, you will get secant squared of x plus secant x tangent x all over secant x plus tangent of x dx. That looks rather curious. Do you recognize what secant squared of x is? Or do you recognize secant x tangent x? Take a look at that. That's really interesting because if you let w equal secant x plus tangent x, then dw will equal secant x tan x plus secant squared of x dx. So you are looking at the integral of 1 over w dw. Same structure as the other ones, which is equal to natural log. In order to save space, I could write w, the absolute value of w, but I know w was secant x plus tangent x. So that turns out to be the integral of secant x dx. Now, given that, I bet you guys could finish up the integral of cosecant of x. This one's going to have a little bit of some negative issues in it, but I think if you let w equal at denominator cosecant x plus cotangent of x, and dw then will be, well, what's the derivative of cosecant? That is just going to be negative cosecant x cotangent x minus, what's the derivative of cotangent? Negative cosecant squared dx. Well, that's just the opposite of what we have written in the numerator. Cosecant cotangent plus cosecant squared. So this lovely thing has become the integral of negative 1 dw over w, which is negative natural log of the absolute value of w, which was cosecant x plus cotangent x plus some constant. So do add these particular integrals to your formula sheet. They are completing now the integrals of all 6 trig functions. Okay. So on to our technique number 2, which is integration by parts. And as I mentioned before, essentially this technique reverses what we know as the product rule. So we'll start off with taking the derivative of a product, uv. We're going to call the 2 functions in this case u and v. So if we take the derivative of the product, we get, of course, first times the derivative of the second plus the second one, v of x, times the derivative of the first. So if we take that expression and now integrate both sides, we can see that u of x, v of x is equal to the integral of u of x, v prime of x plus v of x, u prime of x dx. But we could actually split this up and say, well, that's just u of x v prime of x dx plus the integral of v of x u prime of x dx. Remember that dv dx, another way of writing dv dx is v prime of x. And therefore, dv can just simply be written as v prime of x dx. That differential of our independent or of our dependent variable is equal to the derivative at x times that differential in x. And that makes sense if you think about it algebraically as well as graphically, that our change in our dependent variable is equal to the instantaneous rate of change at whatever point of interest times the change in our independent variable. So if that's true, dv could replace v prime of x dx. And also du could replace u prime of x dx. So a shorthand notation for this, rather than putting all these x's in kind of clutterground notation, would be to say, if we bring this guy down here and say, well, uv equals the integral of u dv plus the integral of v du. Or, if we move a few things around, the integral of u dv equals u v minus the integral of v du. And that actually is the phrase, it's kind of the key phrase for integration by parts. So say it with me right now. Yes, I'm serious. All together now? Are you going to do it? Here's what I want you to repeat. The integral of u dv equals uv minus the integral of v du. All right? Ready? Say it. The integral of u dv equals uv minus the integral of v du. You have to be able to say that in words or in mathematics. That is a known formula for integration by parts. And hopefully what it does is it transfers the difficulty from this integral, which is kind of a weird product of some function and the derivative of another function. It transfers the difficulty to this product, which should be easier to integrate. Okay? So given a product of a function and another function's derivative, which was really the product of dissimilar functions, okay, when we see the product of dissimilar functions, this is what we're going to use. We're going to use parts, okay, and those dissimilar functions will be one function times the derivative of another one equals uv minus the integral of v du. If this second integral, the integral of v du, is not easier to integrate, we have done parts incorrectly and we'll have to go back and do something else. Okay? So on your next slide or one of your templates in there, you have this term LIATE. That's a really, really helpful selection for choosing what your function u will be. Okay? The L stands for logarithmic functions. Log functions. So if there's a log function, you choose it first. Second choice would be inverse trig. Third choice would be algebraic. And fourth choice would be for trig, and last exponential. So that's your priority when you let u be one of your functions as part of that product of dissimilar functions, go through this ordering: log, then inverse trig, algebraic, trig, and finally exponential. Okay? So let's work some examples. Number 1. I don't know if your manuscript has been changed to x cosine of x dx, but that's what number 1 should be if it is not already. So we are going to integrate x cosine of x dx. We start by letting u equal, well, is there a log function? Nope. Inverse trig? Nope. Algebraic? Yes. My algebraic function is x. Now, if you remember that formula we have for integration by parts says that the integral of u dv is equal to uv minus the integral of v du. So if we let u be our x, then dv will be cosine x dx. dv equals cosine x dx. So therefore, this function should equal, now, if we have u, we also need to find du, and we also need dv, or excuse me, v. So if u is equal to x, du will be 1 dx, and if dv is equal to cosine x dx, then v should be sine of x. So this function, or this integral of x dx, x cosine of x dx, becomes u v, which is x sine of x, minus the integral of sine of x, which is v du. And notice, this is far, far easier to integrate than was x cosine x, our initial product. So this is equal to x sine x plus the cosine of x plus c. On to the next example. X squared sine of x. So let u equal L-I-A-T-E, remember, L-I-A-T-E. Log, nope. Inverse trig, nope. Algebraic, yep. X squared. Then dv has to be the rest of the stuff, which is sine of x dx. And then du will equal 2x dx, and v will be negative cosine of x. So this integral becomes, let's see, the integral of u dv is equal to uv, which is x squared times negative cosine of x. So that's uv minus the integral of v, I'm going to make that plus, du times 2x dx. So I'm going to put the 2 out in front and the x right here. Ha! But look at that. We actually just did this one. This integral is again a product of dissimilar functions, but it is this lovely thing right here. So the final solution to this would be negative x squared times cosine of x plus 2 times that stuff, 2x sine of x plus 2 cosine of x plus, now I'm taking 2 times it, so I'll say c sub 1. A different constant than what was used in number 1. Okay, hold on to your horses, because here comes another formula. Because we have not had the integral of ln of x yet, but we will after today. And remember that this lovely thing, even though it doesn't look like a product of dissimilar functions, actually can be done using parts. Just remember that, because you will forget this formula and you may want to rederive it sometime in the near future. Ahem, ahem. So we'll do it by parts. Let u equal, oh, there's a logarithmic function there, so we will let u be equal to the natural log of x. dv then will be dx. And we go backwards and say, well, du then is equal to 1 over x dx. And v is x. So this, the integral of u dv, is equal to uv, which is x ln of x, minus the integral of v du. So that is x times 1 over x dx. But that becomes x ln of x minus the integral of 1 dx. But the integral of 1 dx is simply x. So add our constant, and we have the integral of natural log of x is x ln of x minus x plus c. So then how would you do the definite integral, where you're just evaluating this thing from 1 to 4? So the integral from 1 to 4 of natural log of x dx would simply be the antiderivative, which is x ln of x minus x. Now I could put a plus c there, but you know it will just subtract out. So I just really want to evaluate that from 1 to 4. And that results in 4 ln of 4 minus 4 minus 1 ln of 1 minus 1. We never leave ln of 1 in our answer because we know ln of 1 is simply 0. So this becomes 4 ln 4 minus 4 plus 1, or 4 ln 4 minus 3. Or you could have ln of 4 to the 4th minus 3, or ln of 256 minus 3. Okay, let's do a few more examples. I'm going to skip what you have for number 4 and just go to number 5. And do remember log, inverse trig, algebraic trig, and exponential for your orders. Now, this too is not necessarily a product of dissimilar functions. You could kind of treat it as the product of an inverse trig and just maybe an algebraic function, dx, 1 dx, but otherwise it's just arcsine. And this, by the way, is not a formula that you need to remember or know a formula for, I guess. So, well, in our selection for u, since we do have an inverse trig, we let u equal the arcsine of x. And then, of course, dv will be everything else, which is simply dx. If the u is arcsine of x du, you all remember what the derivative of arcsine is? That's right, it is 1 over the square root of 1 minus x squared dx, of course. And v is equal to x in this case. So this integral, and I'm going to use this space up here since I'm running low on room here. This integral, which is u dv, is equal to, again, say it with me now, uv, which is x, arc sine of x. So uv minus the integral of v du. Oh goodness, look what we get. X times 1 over the square root of 1 minus x squared. Ick. What are we going to do with this thing? Another integration by parts? Well, look closely here. You do not have a product of too many dissimilar functions. In fact, if you look at that, we have an algebraic function of 1 minus x squared in the denominator, and we have x in the numerator. This lends itself to a wonderful application of, you got it, substitution. If we let w equal 1 minus x squared, dw will equal negative 2x dx. Therefore, x dx, which we have, x dx, is equal to negative 1/2 dw. Perfect. So that lovely thing becomes minus, I'm just bringing that one down here, minus the integral of, I replace x dx with negative 1/2 dw, so that's plus 1/2 the dw, and 1 over the square root of 1 minus x squared, which is w. And that we would be able to anti-differentiate. Now, in the interest of saving time and my recording space, I'm going to say we can continue that one later because we know how to do that. So how would you go about doing number 6? Again, is it really a product of dissimilar functions when we have x times x minus 2 all raised to the 4th? I would say probably not. So I would probably let w equal, that inner blob of a function, x minus 2. And then dw equals just simply dx. But we still have an x here, so I'm just going to let x equal, if w equals x minus 2, x would clearly be w plus 2. So this integral becomes the integral of, the x is w plus 2, and then the x minus 2 is simply w, and we have that to the 4th dw. Now remember, we cannot use those x limits when we are working in w. So you can either leave them blank or you can change them. And I think today I will change them for when x is 0, and x is that 0 down there, w will be negative 2. And when x is 2, w will be 0. So now this integral becomes the integral from negative 2 to 0 of w to the 5th plus 2w to the 4th dw, which when I anti-differentiate it, I get 1/6 w to the 6th plus 2/5 w to the 5th, evaluated from negative 2 to 0. And we can calculate that later. As long as we get to a point where we know what the answer, how the answer can be calculated, we're good. Okay, let's just do 1 or 2 more examples and call it good. This is a really unique kind of integral. If you take a look at that one for a minute. I'm going to ask you guys to hit pause and try that before I work it. Okay, because it is not readily evident what to do. So did you hit pause? Go for it if you didn't. So if you already tried letting u equal x squared, letting u equal x squared, or excuse me, u equal x cubed, and dv equaling ex squared dx, you ran into some difficulty, in part because when you let dv equal e to the x squared dx, you're going to be unable to find the function whose antiderivative, or whose derivative, excuse me, is e to the x squared. You're going to have trouble anti-differentiating e to the x squared, aren't you? That's not good news. So we are not going to run it like that. Instead, what I suggest you do is write this another way and say, well, that's just the integral of x squared times x times e to the x squared dx. And watch how this can help you, because if you now let u equal x squared and dv be equal to x e to the x squared dx, then now you are able to find what du and v are, because du will be 2x dx, and v is going to be equal to, well, you may have to take this off on the side and say, well, what is my integral of x e to the x squared? Well, you could kind of play around with this and go, well, I know if I differentiate e to the x squared, I'm going to get e to the x squared times 2x. So the x is there. I need to just put a 1/2 in there. So now this integral becomes, that's the integral of v du. That's equal to, remember, say it with me, uv. So that's x squared e to the x squared over 2. That's uv minus the integral of v du. So I'm going to 1/2 e to the x squared du. It's going to be 2x dx. And I'm going to take out the 2's. Might as well simplify it right away. So I get x times e to the x squared. How are we going to do that one? Okay, I'm just going to come on over here on the left-hand side and say I need to integrate x e to the x squared dx. Do I do that with parts? Or do you always look for substitution first? Ding, ding, ding. You bet. Let w equal x squared, then dw will equal 2x dx. And so x dx is equal to 1/2 dw. And this integral becomes 1/2 the integral of e to the w dw, which is simply 1/2 e to the w, which is x squared, plus some constant. So I can bring that over here and say that's 1/2 e to the x squared. And I have in front x squared e to the x squared over 2 minus that. And I can't forget my plus constants. That is my final result for that integral. I would like you to just take a few minutes and take a look at number 9 and discuss with your table partner what you think is wrong with this. What's wrong with this statement? Especially if I let u equal 1 over x, dv is equal to dx, v is equal to x, and du is equal to negative 1 over x squared. Have I made some mistake in my setup of this integral via parts? Well, I'm gonna, if you haven't paused it, do pause it and talk about this for a minute. Okay? Probably right about now. And the answer is absolutely nothing is wrong with this setup. Nothing at all. Why? Because integrals of a function vary by a constant. And so when you set this integral up using parts, letting u equal 1 over x and dv being dx, and then v is the antiderivative of dx, which is x, and du is that, and you get the integral of u dv equals uv, which is 1 over x times x being 1, minus the integral of v du, you actually get that. Your assignment for tonight is posted. There's just a handful of problems regarding parts. It is posted on Moodle, and it actually is called Section 10.1 Parts Problems. So you'll need to get into Moodle and just print out that handful of problem on parts. I hope to see you tomorrow. Take care and good luck.